In this video, we're going to review two topics that are frequently tested on the AP test. The first one is reference frames and understanding how to solve problems depending on your frame of reference. And the second topic is two-dimensional vectors. So up until now, all of our motion has been in one direction, and starting then when we come back to class, when I see you again next time, we're going to talk about what if I didn't just move left and right or up and down? What if I threw a ball so that it traveled up and down across the room and left to right across the room, which is a two-dimensional vector. The first idea we're going to talk about is this reference frame, or sometimes it's called a frame of reference. Every problem that we set up this year is going to start with a frame of reference. Just think of it as your point of view for the problem. When we're setting up a frame of reference, we're trying to define four things. The first one is, where is zero? What location in our problem are we going to identify as zero? The second question is, when is zero? So at what time will we start our clock or our experiment? The third question is, how fast is zero? So like you sitting in a chair is often 0 miles per hour. But if we would pick a different reference frame, while you're in your chair, remember the earth is constantly spinning. So maybe we want to say that you're actually moving thousands of miles an hour rotating around the earth. So we're going to decide what is our reference frame that we call zero. And the final choice, or frame of reference that we have to decide, is which direction is positive. Lots of times positive will be up or right, but sometimes, like maybe we're watching something fall down, maybe we want the ground to be positive. So these are all things that we need to decide as we look through these problems. So here's a couple practice problems to this idea about reference frames. The first question I came up with was, what sort of reference frame, if you're trying to measure your height, what kind of reference frame do you use? Well, usually time and velocity don't matter, but we need to define what we call zero and which direction's positive. If you're measuring someone's height, you can kind of see in this picture over here, but usually you call the ground zero and you call up positive. You usually measure someone's height from the ground up. You technically could measure from the top of their head down, but that's just not a typical reference frame, not something we'll do frequently in this class. Here's another question. What sort of reference frame would you choose if you go jump off a cliff? This one, people could have a lot of different answers, but maybe you want to say, okay, let's call the ocean where they hit. Let's call that a height of zero. You could, if you want to, call the cliff where they jumped from. You could set up a reference frame where maybe that's your height equals zero. Or maybe they jumped from this other position on the cliff. Probably your default would be to say, well, the positive direction is up. But there could be a way that you could solve this problem where maybe you say, well, this guy is definitely not pointing up. Maybe the ground, like pointing down, is actually positive, depending, because in his frame of reference, he's moving down. That's his direction. Again, for the time, maybe you want to start it from the moment he jumped off the cliff, or maybe you want to know how many seconds until he will reach the ground. So depending on what kind of question you're asked, we're going to increasingly start practicing the skill of choosing a reference frame. Today, I just want you to try to look at problems and think about different locations you could define as zero, and we'll move on from there as the class keeps going. It's a cool thing and a frustrating thing about this class that there's almost always more than one reference frame that you could use to solve a problem. We just want to practice using the ones that make the problems easier to solve, not harder. I kind of talked about this at the beginning of the video. We could say, are you moving right now? Most likely you would answer zero, or you would answer no, I'm not. Unless you're dancing around while you watch this video, then good for you. But remember, we're on the planet Earth, and Earth is rotating. Every day we rotate around itself, and every year we make a lap around the sun. So depending on the reference frame, you could make an argument that you are moving or you are not moving. Okay, this next question says, what sort of reference frame would you probably choose when describing a ball that's rolling across your lab table? So here, I'm going to draw a little picture to try to help. So most likely, if a ball is moving across your lab table, you would say that the direction the ball's moving is 0. Or not 0, is positive. So even if the ball was moving to the left, you'll probably still say that whichever way the ball is moving is positive. You also almost always will call the height of the table 0. There could be a scenario, though, maybe we're interested in the ball as it rolls off the table onto the ground, where maybe you would want the ground to be considered a height of 0. That where is 0 depends on what is the ball doing when we're studying it, and what would make the most sense for the whole picture of the problem. So again, on all of these slides, there's not a right or wrong answer. I just want you to try to think about different ways that you could set this up, and we'll practice more when I come back and you can watch this again. In terms of when is 0, most of the time you'll start the clock when you let go of the ball. But again, if our experiments, well, what happens when the ball falls off the table? Maybe we want to start the clock when the ball gets to the edge of the table. So these are all different things that we're going to consider when we're talking about a reference frame. And again, there's not really a right or wrong answer unless the College Board clearly tells you to solve something from the reference frame of, and they define it. But other than that, you're going to pick a scenario that will make it the easiest to solve the problem, given the question we're looking for. Once you've defined reference frames, it makes another question. The next skill we're going to add to this is defining relative motion. And that's the idea of looking at how is something moving relative to you. This is, I think, easiest to just look at some examples and try them together. Some people love these, some people hate these. Oh, I already said this. Sorry. It's important to pay attention so that you can understand if two objects are moving. Are they two objects coming towards each other? Are they moving away from each other? What's going on? Okay, this picture looks overwhelming at first. There's a lot of little creatures going around in this scenario. So let's just back up and look at one thing at a time. So first I have a train, and that train is moving to the left at 10 meters per second. On the ground is a squirrel that's standing on the ground watching the train go by. On the train, I made a dog sit on top of the train, and it's not moving, but it's moving with the train, like it's on the train, traveling at 10 meters per second. You can think of the dog and the train as one item. And then we've got this bird that's flying backwards at 5 meters per second. So this is kind of weird to look at, but there's a dog on the train. The dog is moving with the train. There's a squirrel chilling on the ground, watching this all go by. And then there's a bird flying the other direction. Here's some practice problems with this of identifying relative velocity. So this question says, what is the speed of the dog, which is at rest on the train, relative to the squirrel, which is at rest on the ground? So think of these questions as if you were the squirrel, or whichever item it's looking at, how fast would you say that's moving? Well, if you're the squirrel, you're at rest, but you're watching the dog travel to the left at 10 meters per second. So speed, remember, that's just a magnitude, an amount, 10 meters per second. If it asked velocity, we would answer 10 meters per second to the left. The squirrel is watching the dog go to the left of it, and it's moving 10 meters every second. Okay, a few more of these. What is the speed of the bird relative to the squirrel? This one's actually easier than the last one was. The squirrel's at rest. It's not moving. It's going to be at the same spot no matter what. But the bird is traveling to the right at 5 meters per second. So the speed is 5 meters per second. The part that would make it velocity is to add that idea of to the right. This next problem has the same picture with the train, the dog, the squirrel, and the bird, but it's asking about two different things. So this one says, what is the speed of the dog relative to the bird? When we're asking this one, it's hard to take a picture in your head, but that's what we're trying to do. And you're asking yourself, how far apart are these two things becoming every second? Well, every second, the dog is going to have moved 10 meters to the left. But every second, the bird will have moved 5 meters to the right. So if you think they start at some 0 point, after 1 second, the dog is 10 meters to the left of where it was, and the bird is 5 meters to the right of where it was. And that will keep going, that the dog and the bird get further and further away from each other. The rate at which that is happening, since the dog and the bird are moving opposite directions, is 15 meters per second. If we were trying to add a velocity to this, relative to, from the bird's perspective, the dog is traveling 15 meters per second away from it, and it's traveling to the left each time. And if we wanted to ask the opposite question, what is the speed of the bird relative to the dog? We would still get the same speed, 15 meters per second, but we would answer to the right because the bird is traveling to the right of the dog while the dog is traveling left of the bird. We can kind of think of these problems as where if you're the squirrel or a person, you can identify, oh, one of you is moving one way and the other's moving the other, and we can see that. But we're going to kind of take our knowledge of the scenario out, the background knowledge that we might come in, where we can say, one of you is moving to the left and the other's moving to the right. And we're just going to look from the perspective of one object in that problem. These are weird and uncomfy, but I know you guys can do it. Oops, I got a little ahead of myself on the last slide. We talked about this. It's the same scenario. It's the opposite question, which I actually discussed on the last slide. What is the speed of the bird relative to the dog? Since the dog is traveling to the left at 10 meters per second, and the bird is traveling to the right at 5 meters per second, the relative speed is 15 meters per second. To add a direction to that and make it a velocity, we would say it's traveling to the right. I kind of talked about that on the last slide. Sorry. Okay, second idea for today is two-dimensional kinematics, which is where we're going to spend the rest of our time this unit. But we're just going to get a little introduction today with the idea of breaking and combining vectors. That sounds stressful. Really what we're going to do a lot of is the Pythagorean theorem, a squared plus b squared equals c squared, and a little bit of right triangle geometry from Geometry SOHCAHTOA. So those are our two friends today. A squared plus b squared equals c squared. And then we're going to recap SOHCAHTOA from geometry class. As we start moving in more than one direction, I'm not going to just throw something up or down. I'm going to throw something up and across a room. We're still going to keep the same idea that anything we've called a scalar only has a magnitude that we're worried about. It only has an amount. Anything that gets called a vector, it's important to us because it has an amount and a direction, and that direction matters. When we're talking about vectors and we're combining things, we're going to look at components. What I mean by that is this is a vector that's going up and to the right. We're going to break it into how much of it is going to the right and how much of the vector is going up. We're going to break the vector into some, usually we'll call it X for whatever's horizontal and Y for whatever's vertical. I do that so that it matches what you're doing in math class. Some things that we're going to need to look at is all of these are going to be broken into perpendicular components. Like you can picture X is running side to side, Y is running up and down. We will not do anything that does not involve a 90-degree angle. When we're looking at these components, there are some aspects about right triangles that you should come into this class knowing. Although I know that for some of you it might be rustier and there might be more cobwebs to dust off than others. So we're going to use the next examples in these notes to do what will hopefully be mostly a review. If for some reason you realize it's not, reach out to me. I have extra resources I can use to help you. So here's an example of displacement. Remember, that's how far are you from where you started. As a vector, a two-dimensional vector. So here's my beautiful dog Tesla. And I'm going to have her run 500 meters at 30 degrees north of east. First, we're going to sketch that displacement. This should probably be a review from geometry. If you're stressed, just reach out to me and I'll get you some help. So I'm going to look at a compass. I got to think in my head, north, south, east, and west. So if Tesla's running 500 meters at 30 degrees north of east, she's going to run in general like up and to the right. And the way that we measure that 30 degrees is it said of east. So I'm going to make a right triangle. And I'm going to measure 30 degrees above east because I'm going north, so towards the top from east. I'm going to swing that vector. Now I'm going to break that run into an amount that's northern and an amount that's eastern. This is where my sine, cosine, and tangent are going to come in. First thing is double check that your calculator is in degree mode. Depending on the math class you've been taking in, your calculator might be in radian mode, and we need to switch it into degree mode for this class. If you don't know how to do it, hopefully somebody in the room can help you. If not, let me know and I'll get you help. And that 500 meters is going to be our hypotenuse. That's the total amount traveled. Now I'm going to think from geometry class. SOHCAHTOA. 500 meters, 30 degrees north of east. I want to find the northern displacement. I'm looking for what's opposite of 30 degrees. I can use sine of 30 degrees equals opposite over hypotenuse. If I want to solve for what's opposite, I'm going to multiply both sides by 500 times the sine of 30 degrees is my northern displacement. Now, if you've already finished pre-calc, you might know what the sine of 30 degrees is. If not, no problem. You get a calculator on the AP test. When you type 500 times the sine of 30 in your calculator, I got 250 meters. So now I'm going to do the same thing with the eastern component. To find what's eastern, I want to find what's adjacent to 30 degrees or next to. Adjacent means next to. I'm going to use cosine. Sometimes I get the question, you could use tangent now that you know what's opposite. You also could use the Pythagorean theorem if you wanted to. I, in general, always try to go back to the things I was given in the problem, but you do not have to. You'll get the same answer either way. So I'm going to do adjacent divided by hypotenuse. I'm going to multiply both sides by 500 meters. And when I push that into my calculator, I got 433 meters. Here's a similar problem with a picture I took of my daughter this summer. She wasn't really feeding ducks, but I thought it looked like she could for this problem. So there's my 2-year-old Eleonora. Isn't she the cutest in her Elmo outfit? Eleonora throws some birdseed toward ducks at a velocity of 2 meters per second and an angle of 60 degrees above the horizontal. So here's my horizontal. I'm going to swing 60 degrees north of that and make myself a little right triangle. I'm going to try to find the vertical component of the birdseed's velocity and the horizontal component. I might use, maybe for today, I'll use V for vertical and H for horizontal. Probably a lot I'll do X and Y, but you can, honestly, you could pick any variables you want. Like you could do whatever you want. To find V, that's opposite of 60 degrees. So I'm going to use sine. Sine of 60 degrees equals opposite over hypotenuse. Very similar. I'm going to multiply both sides by 2 meters per second and put that in my calculator. 2 times the sine of 60. My velocity is 1.7 meters per second. To find what's horizontal, that's what's adjacent. So I'm going to say cosine of 60 degrees equals my horizontal divided by my hypotenuse. I'm going to multiply both sides by the hypotenuse and plug that into my calculator. 2 times cosine of 60, I got 1 meter per second. This is going to be an important step that we need to be able to do quickly as we move on to our next examples that we'll get to as this unit goes on. Okay, now we're going to talk about combining vectors. The first two examples were breaking vectors. Now we're going to combine them. So a mail carrier is going to leave the post office and drive 22 kilometers north, then drive 60 degrees south of east for 47 kilometers. We're going to find her total displacement from the post office. I always would like to start with a picture. I'm going to get me a compass in case I'm struggling a little today. So I'm going to go 22 kilometers north. And then I'm going to go southeast at 60 degrees south of east. So it's going to be kind of like this. Probably not to scale, but it's my attempt. 47 kilometers. And I'm going at 60 degrees south of east. To find displacement, I'm going to always use some skills to bring this back to a right triangle. So I can say, I know I traveled up 22 kilometers. Then I did some version of traveling to the right and down. And I want to ask myself, I'm going to make a little baby triangle. Well, I don't know if it's baby. It's 47 kilometers long. That's kind of a long triangle. But I'm going to make a right triangle that has some component that's going side to side. I'm going to call that X. And some component that's going up and down. And I'm going to when I'm combining, I'm going to try to look at individual vectors. To find the amount that's side to side, my X, I'm going to use SOHCAHTOA again, specifically cosine. Cosine of 60 degrees is adjacent over hypotenuse. So X is going to be 47 times the cosine of 60 degrees. That part of the triangle that I labeled X is 23.5 kilometers. Now I'm going to find Y. I'm going to use sine, opposite. Sine of 60 degrees is opposite over hypotenuse. Y is going to be 47 times the sine of 60 degrees. And I'm going to get an answer of 40.7 kilometers. Now, again, so I have now my components. I'm going to try to combine these terms. So I can say, okay, in the total trip, I went up 22 kilometers, and then I came down 47 kilometers. So my total amount in the vertical direction is I went up 22, and then I went down 40.7. 22 minus 40.7 is negative 18.7. So my total amount that I traveled down was 18.7 kilometers. My total amount, or south, we could say that. My total amount that I traveled east and west was 23.5 kilometers. Here's where the combining comes in. I'm going to draw a new super triangle that shows that I went down 18.7 kilometers. Whoa, sorry. And that I went over 23.5 kilometers. And I'm going to find my total displacement. I could show this on the original triangle. Let me see if I can. I'll get the highlighter out and switch colors. On my original triangle, I'm making it with this that I just highlighted in blue. Here's my total amount up and down, total amount side to side. I'm looking for the hypotenuse. My displacement is how far am I from where I started, with one extra thing, with a direction. To find the displacement, I have two legs of a right triangle. I can use a squared plus b squared equals c squared. 18.7 squared plus 23.5 squared equals c squared. So 901.94 equals c squared, which means c is 30.03. I'm going to drop those digits. 30 kilometers. To find a direction here, I'm going to use an inverse sine, cosine, or tangent. In this case, if I'm trying to find the angle, by the way I drew this picture, I know what's opposite of that angle and what's adjacent of that angle. I'm going to use tangent. I'm going to zoom out again. Sorry for the weird perspective here. The tangent of my unknown angle. Let me back up again. I'm doing something else for the first time. This symbol that I just used is a Greek letter called theta. We will use that almost exclusively in this class to describe angles. It's the College Board's favorite variable for an angle, theta, Theta. But the tangent of that angle is opposite over adjacent. To find out what that angle is, I'm going to do an inverse tangent. And so I'm going to type on my calculator second tan, 23.5 divided by 18.7. And I got an angle of 51.5 degrees. Next I know this is a lot, but you guys can do it. Next thing that I'm going to do is figure out how to label that. So this angle, it's based off of the south, and then I'm swinging towards the east of this. So this answer, I would say that this is east of south is how I would report that answer. So my final answer would be 30 kilometers at 51.5 degrees east of south. If you're asked for displacement, and unless it explicitly says you don't need the direction, you need both things, and an amount and an angle. Because I know these are really long, that kind of was a lot of process, you won't do a ton of these on the homework, but it is a skill that's important to be able to have down. Okay, here is another story problem. It says the designated course for a 6-kilometer road race has the runners going 4.5 kilometers west, 4.5 kilometers west, and then 1.5 kilometers north, where the finish line is located. So here's our finish. A less than honest contestant in the race, oh no, runs 2.5 kilometers west. Maybe this would be me. I think this is a lot of running. And then decides to head straight towards the finish line. What distance does this wannabe actually cover during the race? Okay, so what I'm trying to figure out is the total amount that this runner actually traveled. If they only ran 2.5 kilometers and then they took off to the start, I'm going to highlight where it's going to come from. I'm going to make myself a right triangle using the part that they cut off. So that right triangle, instead of running 4.5 kilometers, they only ran 2. So they cut, or 2.5. So they cut off 2 kilometers from their race in the horizontal direction. But they still need to run 1.5 kilometers up. And I'm going to make a little right triangle that I'm going to highlight again so you can hopefully see. This is what I'm interested in. What distance did they actually travel when they should have been going over 2 and up 1.5? I just drew a right triangle, and I know the 2 legs of that right triangle. So this is not too bad to find. I can do a little Pythagorean theorem. A squared plus b squared equals c squared. 2 squared plus 1.5 squared equals c squared. 2 squared is 4. I'm pulling out my calculator for 1.5 squared. 6.25 equals c squared. Now I'm going to take a square root, and I got that C equals 2.5. So this runner actually went 2.5 meters over and then went on a diagonal 2.5 meters. The distance they actually covered was only 5 kilometers when they should have run 6. So they cut off a kilometer on their race. Cheating runner. Don't do that. For the rest of class today, I want to give you some chance to practice that. There's a Classkick assignment that you can look at and practice, and there's also 2 assignments on this website called Physics Aviary. You'll go into those, you can either scan the QR code or click the link, but they'll take you to problems that every time you refresh the screen, you'll get different numbers, but you can try a problem with relative velocity and a problem with combining vectors. They are in the practice assignment, so they're not for a grade. They're just recommended, especially if you have some cobwebs with dusting off some of these that geometry skills. But you guys are great. I miss you and wish I was in the classroom instead of at curriculum writing today.